Welcome everybody in the lecture hall on Zoom from the future. So today we are going to finish, hopefully, the lecture on index construction. And before we start, I have a few questions to ask you on the clicker. Here's the first one. How many terms or types, because we saw that if you group in equivalence classes, then you put types, can a 4-7 B plus tree of height 3 contain at least, right? So what I mean with the height is 3 means 0 would be if there's just the root, 1 means there's the root plus children, and then 2, 3, you add more layers, right? That's the convention. So a 4-7 B plus tree, height 3. How many terms can it contain at least? That's the minimum that I'm asking. Last time I asked for the maximum, remember? Now I'm asking for the minimum. Of course, as you can imagine, if now I'm asking the minimum, it means that you need to remember something that makes it different than computing the maximum, right? So there is a little trap in there. So you have to avoid that trap. All right, 2 of you got it right. Who is it? Are you in the room? Yes, one here. 2, right, congratulations. So how did you do it? Maybe we can throw one of the catch box. You, for example. Yeah.
Well, the root has 2 children, and then we have 4 children, and we repeat it 2 times. So we have 2 times 4 times 4 is 32.
Mm-hmm.
And because the minimum number is 4 children, we have a minimum of 3 keys. So
yep, exactly. That's correct.
32.
So there are 2 traps. Technically, the first trap we already knew from last time is that when you the final number, you have to remove 1 because you have the number of keys, that is the number of children minus 1, right? You have to imagine virtual children that the leaves would have, right? So if you have 3 keys, they would have virtually 4 children, which is the minimum. So this is why 3. And the second trap was indeed that the root has at least 2, right? It's allowed to have less than 4, right? Why not 1? Well, if it were 1, then that wouldn't be height 3. That would be height 2, right? Because then the root would be unnecessary. So indeed, it's 2 times 4 times 4 times 3, which gives you 96, either in your head or with a calculator. All right. So that was the first question. Congratulations, both of you. Now, maybe this one I keep for later. Here's another one. I'm asking you for the Soundex representation of the word paper. So of course, there is this mapping from the letters to the digits, and I'm going to share it with you, because of course I don't expect that this is something you know by heart. So here you go. So paper, right? So these are the letters, and this is how they are mapped to digits, right? But you need to remember how we do this mapping. So paper, P-A-P-E-R. Who has it? Who is done? Do you still need the projection? Can I switch back to the clicker question? But this is the slide we had it last week, right? So this is a slide that you can find also in the lecture. So paper. Let's look at what you said. All right, and the majority is correct. So how is this done? Well, first, you need to remember that the first letter is not encoded to a digit. So the first letter, P, stays that way without being encoded into a digit. So it's P, and then you have A, that's a 0, then another P, that's 1, then E, that's 0, it's a vowel, and then R is 6. So at that point, you have P0106. Now we eliminate duplicates, but duplicate meaning 2 digits that are the same and that follow each other, but there's nothing like this in that case, right? P0106. Then we remove the zeros. So we have P16, but then we need 4 in total. So we need to pad with zeros where we are, we have less than 4. And since we only have P16, we need to add a 0 at the end, and thus we get P160. And probably the mistake with 116 had to do with the fact that the first one probably comes from P, the letter P, right? But since there's already the letter P, you don't encode it again with the digits, right? Okay. Then here's another one. What is the Jacquard's coefficients on the sets of 2 grams associated with computer and computer? 2 grams. Don't forget the dollar, right? You need to put a dollar at the beginning and at the end before you take the K grams. We have 9 answers so far. Sometimes the easiest is to just take a sheet of paper or write in a textbook somewhere all the diagrams, and then for both, and then you take the intersection, how many there are in common, how many there are in the union. Let's see the first answers. So 0.7 seems to be a majority. that would be 7/10. 0.777, that would be 7/9. You know, when you divide by 9, just repeats the same digit all over again. Then 8/10 or 8/9. And the majority is correct. It is indeed 7/10. How do I do that? So I can even do it live without drawing anything. So how many bigrams are there in computer? Well, there is this trick that there's eight different letters in there. So that would give us 9 bigrams, right? Because there's no duplicates. There is no repetition of the same sequence. So we have 9 bigrams in computer. And in computer, how many new ones do we have? Well, the only one that would be new is CM, right? So that would give us 10 in total. So we know the union has 10 bigrams in total. Now, I can either look at the intersection and count them, but what's easier is to look at those that are not in the intersection. So what is not in the intersection? On the left, it's CO and OM that are not on the right. And then on the right, you have CM that is not. So there's 3 of them that are not in the intersection. And the others, 10 minus 3, that's 7 of them are in the intersection, which gives us 7 divided by 10, which is the Jaccard coefficient. All right, so congrats on the answer. And hopefully the explanation is convincing for everybody else. Then another one about the edit distance. If I edit this, I compute the edit distance between a word and itself. I take the same word. So obviously the distance will be 0, right, between a word and itself. But what about the table, the dynamic programming square that you would draw for this? Does it have zeros on the diagonal? Does it have zeros all around the borders? Is it filled with zeros all over the place, or does it have consecutively decreasing integers on the diagonal, all the way down to 0? So you remember this dynamic programming, right? We write one of the words on the rows, the letters are on the rows, the other one, the letters are on the columns, and then we use dynamic programming to populate this square with integers. All right, we have enough answers, and the majority is correct. It has zeros on the diagonal, right? Because the diagonal is comparing a prefix with exactly the same prefix, so it has zeros. Fields with zeros, no, because if you're outside the diagonal, then you would be comparing different prefixes, right? So this is why you don't have zeros everywhere. Not yet. Still, I have to give you the lecture first, and then I'll ask you how much you understood. Okay. This one. And it's recording. All good. All right, so now let's continue. So we've looked at this first-class citizen, which is the standard inverted index, which is the center of attention for Boolean querying. And every other index is basically a variation of that one, right? We extended it with bywords, we extended it with permuterms. We have plenty of ways we can do that, also with positional tokens. But basically, the standard version is this one. So you remember we have the terms that are pointing to the postings lists that are the document IDs associated with this term, which are actually pairs term documents, but the term is the same on every row, so that's why we don't repeat it, and we only have the document IDs. And in the purple rectangles, we have the so-called document frequencies, which is nothing else than the size of the postings lists that there is on the right. So that's the standard inverted index. You did it in Python, in a Jupyter notebook. But of course, it was easy because the data set was small enough that you could actually do it in a straightforward way with Python. And the purpose of this lecture is to start worrying about how do we do that if it doesn't fit in memory, or even if it doesn't fit on the disk. How do we build then the standard inverted index? So there is a first prerequisite that I presented to you that will be useful throughout this lecture, which is the notion of term IDs. because in here you only have document IDs, right? But the terms, they are just the terms. We didn't replace them with integers. But in fact, while you build the index, in some of the techniques, you actually do want to replace the terms with integers as well. So here I put a small t in front just to distinguish from the document, but essentially it's an integer. And so when you look at a posting, these are all postings, right? But since these are postings that are in the wild, so to say, they are not part of the index. So since they are in the wild, then these postings must have the mention of the term in of the documents. So we use the document ID, but we also use the term ID plus somewhere else some mapping between the ID, the term ID and the actual term, right? But that way we save space because the term is only stored once, and then we just use the term ID in the postings. All right. So again, what's important to understand is that this and this is pretty much the same thing. It's just that here they are nicely ordered, grouped by term and organized in increasing order. Here they are in the wild. This is during the construction of the index. We just have postings all over the place in the form of term document pairs. All right. So now I'm going to proceed to the first way that we can build our index in an optimized manner if it doesn't fit in the computer memory. And this is called the blocked sort-based indexing, or BSBI. Some people call it BSBI. So if you hear BSBI, you know that this is what it means. So of course, that sounds a bit scary in terms of how it's called, but let's just look at it and we'll see that it's actually simpler than it seems. So imagine that we don't have enough working memory. We have enough disk, right? So assume we have enough disk, but we don't have enough memory. So a first very naive way of doing it would be to say, okay, who cares about the memory? Let's just use the disk, right? Let's process everything on disk. So technically we could, right? We can just write back everything. Every time we do something, we just manipulate the term documents on disk and so on. So technically, if we take, for example, a 12 terabyte drive, if you do the calculation, then you need to both store the collection and the postings while you are building the index. So if you do the calculation, I think the factor was roughly, if you have 1 gigabyte of space for the collection, then you need 1.2 gigabyte for the postings. So let's assume that. Then it means that you can fit on the disk 5.3 terabytes to store the actual collection, right? So these are the actual tokens. If you assume, in that case, 530 billion tokens. And you assume a specific average size, of course, for every token, maybe 10, for example, 10 bytes. And then why not 12? Because we need space for the index construction. So we have these 5.3 terabytes used for text, and we can use the remaining 6.7 terabytes for these intermediate postings that fly all over, right? So of course, I computed it in order to fit exactly. So here we have barely enough space to fit that, right? This is the maximum size of a collection we are able to index with a disk of that size. So of course, it's restrictive because this is only 5.3 terabytes, right? You cannot index the entire internet with that, right? It just doesn't work. So there is another reason, actually, for not wanting to do it, is that the disk is going to be awfully slow, right? You keep writing and reading from the disk. You have the latency every time, especially if it's an HDD for more capacity. So this is just going to be intractable. You cannot use a disk in practice. So we care about speed. So we need to be a bit smarter than that. We can just not do everything on disk. But there is something, a trick coming from big data, that's called batch processing. Batch processing. And the idea is that we want to minimize the interaction with the disk, right? We want to interact as rarely as possible. But when we do, we are serious about it. Like when we do interact with the disk, then we read and write a lot of data, right? So this is actually what batch processing is, right? So we do most of the work in the memory, and occasionally we read and write large amounts from the disk, but that way we minimize the latency effect, right? And again, I insist, few requests, that's because of the latency. If you ask the disk only, let's say 10 or 20 times, it's going to be faster than asking 1 million times for just a few bytes, right? So this is the reason. So this is called batch processing. So how do we organize ourselves? Well, imagine we have this absolutely gigantic collection of documents. We just partition it, right? We cut it into small partitions, and each one of these partitions is called a batch. The word batch actually dates back, well, I'm not sure if that was the first use of it, but it dates back to the time that we didn't have computers like this, you know, that would just run in an interactive way. Back then, maybe, I don't know, 40, 50, 60 years ago, the PhD students right here at ETH who were working on their thesis and they needed to execute programs, they had to use these punch cards, and they would just write their code in zeros and ones on the punch card, and then they would bring it to an office somewhere. They would bring the punch cards and leave it there and come back the following day. And so basically, in the office, everybody brought their punch cards, so you accumulate them, and then maybe at the end of the day, they just take them and execute them all. This is called a batch. They take a batch of these punch cards and just go ahead and execute everything. Of course, as you can imagine, it was complicated because then there was obviously bugs like there is today, except that every time you needed one day to try again and again and again. So it was very painstaking to do. So now we have the luxury of having our computers and laptops that tell us right away when there is a bug. All right, so this is where the word batch basically comes from. So we divide these huge collections that might have billions of documents in batches. I don't know, maybe 1 million documents per batch, just an example that what it could be. So if we have a billion documents, we could have 1,000 batches of 1 million documents each, right? So the little icons that you see here, the little rectangles, these are the actual documents. So we cut them in batches. And then what do? Well, we process them one by one in memory. Why can we do that? Because we picked the size of the batches in such a way that we can process them in memory, right? So we take this first batch and then we build the term document pairs, so the postings. We just sort them, do whatever we need to do, and come back to the details later, but we just deal with that first batch as if it were the only batch at all, right? The rest of the collection doesn't exist right now. And then we go ahead and proceed with the second one. So obviously we might write back to disk something that we did for the first one, right? But we proceed to the second one and do the same, as if it were the only collection in the world and we don't know about the other batches, right? Then we proceed with yet another batch and yet another batch, right? So there is this notion of sequentially, right? We still do one batch after the other, but for each batch, the memory is enough. Right. This is what matters. All right. And every time, as I said, we write back, every time we process a batch, we write back some intermediate results to disk. What could it be? Well, it could be the sorted term document pairs. It could be directly some form of a raw standard inverted index, but just for that batch, right? And so we write something back to disk every time. And once we have processed all the batches, we have this mini raw proto standard inverted indices, if I can call them that way, but for every batch. So of course, we are not happy with that quite yet, right? Because we want the standard inverted index for entire collection, not just for every batch, right? So we need one last step at the end. We take these intermediate proto standard inverted indices and we merge them. And this we can do in memory. I'll tell you how. Of course, I'll come back to why that actually works, even if the size is greater than that of the disk. And then we have our final index on the disk, and that's it. And now we're happy, of course, because you might remember that it's fine to have the standard inverted index on the disk. What do we want in the memory? What we want in the memory are the upper levels of the B+ tree that organizes the terms. But the levels at the bottom, it's fine. They can be on disk because you will anyway only read what you need when you query something, right? And the same for the postings list. They can be on disk. You will only read the ones that you need, right? Okay, so we have the final index. Everybody's following? Yes, okay, good. So now I'm just going to zoom in. I'm still with BSBI, the first technique. So I'm taking one batch and I'm going to process it. So what do? Well, I start reading the batch, I tokenize, I lemmatize, what is it called? I stemize, I'm not sure if that's called that way, but the Porter stemmer or everything we saw 2 or 3 weeks ago. And then we get our tokens. And then we can group them in equivalence classes, and then we finally get the actual terms, right? So once we have done all of that and process it as if it were the whole collection, we have term ID, document ID pairs into memory, right? Because of course, whenever I have a term, I maintain that term ID mapping, right? So every time I see a new term, I'm just creating a new term ID, adding it to the mapping, and then I create my term ID, document ID pair into memory. Right. So it's very efficient because it's just a pair of integers, right? So every posting, if it's 32 bits each, it's basically 64 bits for each posting. Okay. So basically, this is what you have in your memory. You basically have the term ID mapping right there. That is rather small. It's just a list of the terms with the ID. And here, this is where it's interesting. You have all of your postings in the wild. Right, totally flying around with no particular order. You just created these term ID, document IDs in memory. Okay. And I insist it fits in memory because the batch has been taken small enough that this all fits in memory. So then we have 2 strategies for that. I told you you can generate the term IDs on the fly. I actually called it strategy 2 here, that every time you see a term, you look it up. If you find it, then you take the term ID. If you don't find it, you create a new one. But there is another strategy that some people prefer, is that they first do a first pass over the entire collection, streaming through the disk and creating the term ID mapping once and for all. Right? So they do this extra step at the beginning just for the purpose of creating the term ID mapping. Right? So either as a first pass or on the fly as you actually creates the postings. Okay. So now we've processed one of the batches. Turns out I called it a block. That's probably coming from big data, but you don't have to worry about that. You can just call it a batch if you prefer. So we process one of these batches. Then we sort, right? And log n, the best algorithm for sorting, right? So we sort all of these term ID, document ID pairs by term ID, obviously, because in the end, we want them in the standard inverted index organized by term, right? But for the same term ID, we also want to sort the document IDs because we also want the posting lists to be ordered, right? So we sort lexicographically, first by term ID and then by document ID. And then I have this nice pile of term ID, document ID pairs that are in my memory, and I can write them back to disk. So that's the first approach, is to just write the pairs back to disk, right? So for now, let's assume we do that. We write them back to disk. Okay. And then I do it for the first batch, for the second batch, for the third batch, I just go with the batches. The only thing that remains in memory is this term ID mapping. This is the only thing I keep in memory, because of course I need to keep consistency between my mapping of term and term IDs, right? So this stays in memory the whole time, and you just keep adding to it. But this now you can wipe out from memory because it's on disk. You just make the memory blank again, and then you proceed with the next batch. Who is following? Okay. So at the end, you'll have written to disk sorted term ID, document ID pairs by batch. So you have a sorted list for batch 1, a sorted list for batch 2, and so on. And now we need to create the final standard inverted index. So what do? Well, we can actually do it by reading from disk in a streaming fashion, meaning we don't load them back to memory. That wouldn't fit necessarily. So we just have a pointer for each batch. Here I have 3 batches in that example. I have a little pointer with some coordinates on the disk that tells me, okay, I'm placing the first pointer on the first pair of the first batch, the second pointer on the first pair of the second batch, and the third pointer on the first pair of the third batch. And then I'm going to merge. And in fact, that's going to be very similar to the union that we did when we queried this Boolean querying, remember? when we have the OR queries, we were computing the unions, we were just traversing in parallel the two lists, right? In fact, we are going to do exactly the same thing here. We just traverse in parallel these things and we just intersect them. So you see, for example, I might see, okay, the smallest one is in the first batch and it's not in the other batches. So I add it here. And then, so I'm taking care of the yellow ones for now, right? There's no yellow one in the second batch, then comes this one. And you see what I'm doing here. I'm already creating the standard inverted index, right? So now I'm not repeating the term ID every time, right? It's repeated in the pairs, right? In these pairs, you have the term ID every time. But when I actually write my standard inverted index, I fetch the term from the term ID mapping. I write down the term and then my sequence of postings like this. So there was this one, and so on, right? So you see, now I'm done with the yellow term. Here, I have all of the postings and they are ordered because of course, the way I traverse, I traverse in order. And now I proceed with the next term right here. And so I continue to write in increasing order my document IDs. There you go. And I'm done with the second term. Now the third term, there is none of it in the third batch. Okay, now I'm done. I'm just accelerating here. Finally, the last term. I just merged. What is the complexity of that? I'm sorting things. Is that O of n log n? Yes? It's linear, exactly. Yeah, it's linear because you're just traversing concurrently. Okay. But there is no, what can I say? It doesn't mean we actually sorted things in linear time because overall it still takes n log n, right? Overall it still takes n log n. It's just that the log n part was in when we were actually doing this. This is where the log n comes from. But this last part is indeed linear because it's just a concurrent traversal and it's as many steps as there are actually term document pairs. Okay, and then we write it back to disk. So again, to summarize, the first step when I treat all of the batches is T log T. And in that case, it's T is the number of tokens, of positional tokens. So T log T in the first step. And the second step is O of T. Then I don't have a log anymore. But of course, if you add the two together, then it's T log T, right? In practice, it feels very much like like O of T. The reason has to do with the constants. It's that in practice, the really large constant is going to be for the O of T. So the second step dominates, and even in the first step, even though it's log T, in fact, in every batch, you're only dealing with a subset of all the tokens, not with all of them. So this is why it doesn't really feel like log T, and it almost feels linear. Okay. But again, it feels because I'm not saying that we sorted things in n, right? It's still T log T, but the feeling. Okay, who's with me? Okay, good. So let's go to the second one, which came later. It's an improvement over the first one. That's kind of a next generation way of doing things. It's called the single pass in-memory indexing. And if you don't like that fancy terminology, you can just call it SPIMI, S-P-I-M-I, SPIMI. All right, so let's see how SPIMI works. So in BSBI, the first one, we processed the batches in this way, just parsing each batch of documents to pairs that are in the wild. Well, the difference with SPIMI is that in SPIMI, we are in fact, for every batch, directly building some sort of standard inverted index. So we do process, of course, the pairs in the process of doing that. But at the end of the batch, when I'm done processing the batch with SPIMI, I actually do have some standard inverted index. This is why I meant with proto standard inverted index, because that's not the final one, but it's just some mini standard inverted index just for that batch, right? What's important here is there are no term IDs at all. We directly use the terms, right? Because we only store them once since we directly build some form of index, so we don't need term IDs. So I build my proto standard inverted index just for that batch, right? So first, the way I do it is probably I want to make it easy to look up a term. So you could either use a hash, for example, a hash map for the terms. and then you sort at the end, right? It takes n log n in the number of terms, and then you sort at the end. Or if you don't want to use a hash map, you can already use some sort of tree map or some structure that already preserves the order from the very beginning. But you still have the n log n in any case, right? Because then it's just that the n log n is while you insert your terms instead of when you sort at the end, right? Okay, but in any case, at the end, we have this sorted list of terms that are themselves associated with sorted document IDs, and we write it back to disk, right? And again, I insist, there is no term ID for SPIMI. And then at the end, we do the final merge, but this time we don't merge sorted lists of pairs. Now we merge proto-standard inverted indices, but you will see it's just as easy, right? You just, again, have the pointers. It's anyway already sorted by terms and by document IDs, so it's really a linear thing to do. So we start with the yellow one, and then we load maybe everything in memory to be faster, and then we put back the sorted list of document IDs. Of course, we could also do it directly on disk, right? But sometimes that probably fits in memory, it's probably easier. And then you proceed with the next term, you merge, then the next term, and so on. And now you have the full-blown standard inverted index for the entire collection that is here. And we did it, okay? But now we did it without any need for term IDs, and it's a bit more efficient, right? So this is SPIMI, that's the second generation way of building the index. Understood? Right. They are very similar, right? It's just that the second one kind of improved over the first one by taking a few more shortcuts and simplified a few things. So in terms of complexity, so first, there is no miracle because there's always this issue of sorting things. But what's important to understand here is that when we sort in the first step, we only need to sort by terms. We only need to sort these terms that are on the left of my standard inverted index. Why not the documents? Because we just increment the documents. It's a counter. Every document gets a +1. We don't need to sort them. We just assign the IDs in increasing order. So this is why we don't need to sort the documents. So this is why here it's an M log M kind of plus an O of T. So if you combine, you get O of T log M. The second step is still linear. And in the end, if you consider that the number of terms compared to the number of tokens is negligible, then again, it feels like O of T, but it feels even more like O of T in that case, right? Okay. It raises the question of what is the relationship between T and M, right? So obviously, if you increase the size of the collections and you increase the number of tokens, then you're going to also increase the number of terms, right? But this question I will answer next week, probably next week, right? So if you consider M to be negligible just for now as a simplification, then again, it feels, what you really feel is that it's linear in the number of tokens. Okay. Are you with me? Should we proceed with the next one? Okay. So the next one is it might be something you've already heard. Who already heard of MapReduce? Who never heard of MapReduce? Okay. So I'm going to tell you what this is, and then we will proceed and use it. This is for the case where the collection doesn't even fit on your disk. The collection is spread over multiple machines. It might be a petabyte of data that you want to index. So here we are literally talking about implementing a Google, right? When we do that, we want to do it with the entire web. Now, MapReduce technically is material from the big data lecture. So I'm basically just explaining it a bit earlier to you what this is, but this is very useful in the context of information retrieval. It was invented by Google in 2004, I think, or something. That was already 20 years ago. And this is, in fact, more or less, it probably changed, of course, with the years, but more or less, this is the way that the web is indexed. So I thought, how do I teach MapReduce? So I thought, okay, let's do something fun. Who plays Pokemon Go? Nobody? Or you? Oh, some of you. Okay. So I'm going to explain it with Pokemons. But first, I want to explain the structure that we have some inputs at the beginning that would be the collection, and we want some outputs that would be the standard inverted index. And the structure of MapReduce, it's an extremely simple framework, actually, that basically says you take the input, you do something on it in parallel, then you shuffle things around, then you again do something in parallel, and then you output. That's pretty much it. It sounds extremely simple, but in fact, it's extremely powerful because it solves a lot of real life problems that can actually be turned into that sort of things. Okay, so this is in essence what it does. But again, so much easier to do it with Pokemon. I actually don't know all the names. I just know this one is Pikachu. So I was on a hunt last weekend throughout the city and collected some of them, but I haven't counted them yet. And I would like to know how many I have of each, right? So I have a few thousands. I was very active last weekend. And so I want to count them. So I can either, just go to my office and count them. Probably going to take me an entire day. I'm not sure it's such a good idea. But what we can do as well is to count them in parallel. So in fact, what I do, I don't do it in this class, but in the big data class, I like to actually bring the Pokemons to the class, and I ask the students to actually do the counting. And so the way that this is done, I'm basically asking for this output for every Pokemon. I want to know how many I have. So what I do is that I bring my Pokemons, I prepare them in batches, right? It means that I have maybe 10 batches of Pokemons, and I put them in plastic bags for things. And so then I distribute them to volunteers, right? So I give them basically in these batches. And then every volunteer, every student is going to take these Pokemons of their batch, and they are going to write down on a piece of paper that I also prepare and give with the list of all the distinct Pokemons. And then for every Pokemon, they are going to write down, okay, I have one of these, 3 of these, 2 Pikachus, and so on and so on. Okay, so this is the output of every volunteer of the mapping task. And then what happens is that some other volunteers among the students, 8 of them, for example, they are assigned Pokemons, 1 or 2 or 3 Pokemons each that they are responsible for. And so what happens is that there is, and we actually did it in the class for real, it was a huge mess, but actually it was very instructive, that then you have this bottleneck part of the whole process where every person who processed these Pokemon batches, you need to cut now in the piece of papers, Pokemon by Pokemon, and you need to hand over all the Pikachus, go to these students, right? And then you do the same. So of course, this is when it's a huge mess because you need to, every single person from the first group need to find each person from the second group. Complexity is quadratic, right? N times M if you want. Okay. And so then in the second group, now that they've collected all the counts for the same Pokemons, so in that case, it's only Pikachu, but maybe the same person can be responsible for 2 or 3 Pokemons. And then we count 1 plus 2 plus 1 plus 3 plus 1, I have 8 Pikachus, right? So this is my output. And then finally, when I get the output from all the persons in the second group, I get my final output. Right? This is how you can count Pokemon. And it didn't take 1 day, it actually only took 20 minutes or something. All right, so this is how it works. Now we have a name for the 2 groups. The first group is called mappers, map. And the second group is called reducers, reduce. So this is where this is mapping, map, and this is reduce. This is where MapReduce comes from. All right. But of course, now we are not counting Pokemons, we are trying to build the standard inverted index, right? So how do I now use this technique in order to build my standard inverted index? You will have the answer in 15 minutes after the break.